Cool. Really? Thank you. Thank you very much, Francesco. Thank you for inviting me here. Actually, it's great to be here in beautiful Florence on this wonderful mountain or hill above Florence. And also this gives me an opportunity to enjoy Italy and even try to look like Italian. In my home, in my town in which I live in Minnesota, St. Paul, Minnesota, being in this outfit would look definitely weird. So, especially in the summer. So, I will be talking about our joint paper with Hisham Sati on mysterious triality. And the story goes like this. Once upon a time at Harvard in 2001, three mathematical physicists, Iqbal, Naitsky, and Vafa, came up with the idea of mysterious triality. They discovered mysterious triality, sort of a set of parallel things happening in two situations, two apparently different and unrelated situations. So this was Iqbal, Naitsky, and Vafa. They posted a preprint in 2001, published in 2002, and they came up with mysterious triality, and that was, they noticed kind of deep parallels between, but still combinatorial parallels between algebraic geometry and physics. More precisely, on the algebraic geometric side, between Delpezzo surfaces and here toroidal compactifications or dimensional reductions, compactifications of 11-dimensional M theory. They notice parallels, basically the parallels start with, or can be briefly described as the presence of hidden EK symmetry in both situations. Okay, and let me tell you a few words about what this is. So on the physics side, when you talk about M theory and its dimensional reductions or toroidal compactifications. On this side, well, in both situations, so roughly speaking, I can say that, look at this diagram E10, Dynkin diagram E10. Is this right? 4 plus 6. Yeah. Look at this Dynkin diagram E10, and in M theory, one can sort of symbolically recreate this diagram by starting with M theory in 11 dimensions, and then considering its dimensional reductions or toroidal compactifications. So you get to type 2A string theory in 10 dimensions, then you reduce dimensions further, you get to 9 dimensions, then to 8 dimensions, and so on, down to 3 dimensions. I don't think that anybody dares to go any further, because we are talking about our space-time, and so even there is some kind of a stretch to say that we live in the 3-dimensional space-time. Now, there is also an outlier theory, type 2b, a 10-dimensional theory, which yeah. Yeah, I was kidding, actually. I know, yeah, people do 2-dimensional supergravity and 1-dimensional. Yeah. Our work also goes down even in the negative dimension, right? But still, it makes sense to look at those things. Yeah. So thank you, Antonio. Yeah. So then on the algebraic geometry side, AG. So you look at Delpezzo surfaces. Yeah, also talking about Delpezzo surfaces seems to be appropriate in this country, more appropriate than in any other country. I don't know if Delpezzo was a great Florentian mathematician, probably not, but Italy is a big country after all. But still, it's nice to get back to Italian school of algebraic geometry. So we start with, it's a series of algebraic surfaces. I will be talking about complex algebraic surfaces. So they have real dimension 4, and you start with B0, which is another notation in this theory for CP2, for the complex projective plane. And then then there is a whole series of those, and you go from one to another by making a blow up of one point on this on the previous surface. So you blow up one point, you get to B1. You blow up another point, you get to B2, and so on. And this goes down to B8 when you blow up 8 points on CP2. You can get the same result by blowing up 8 points on CP2 in general position, and these are called Delpezzo surfaces. You can keep blowing up points, and so you can keep going down in this shady area, but it will be you will obtain surfaces, but they are not called Delpezzo surfaces in classification. So there is a notion of a Delpezzo surface. They are classified like this, but there is one outlier Delpezzo surface, such that if you blow it up, so here the dimensional reduction of type 2b string theory gave us the same theory as the dimensional reduction of type 2a string theory. And so you get to 9-dimensional theory on both sides in the same way. Similarly here, you go from an outlier Delpezzo surface, which is the Cartesian square of two complex projective lines, and you blow up one point on it, and you get to B2. And then keep blowing up points, you go this way. And so this is, so here B k plus 1 is what is often denoted bk tilde for the blow up, for the space of blow up. And this is the result of blowing up one point on bk. And so those arrows mean going from bk to bk plus 1. Not really maps. The maps go backwards. There is a map from the blow up to what you were blowing up. Okay, so in algebraic geometry there's also the sequence, but if this were the points of parallels, that wouldn't tell us much, that wouldn't be so convincing. They actually wrote quite a long paper, maybe a 40-page paper, convincing that there are deeper parallels between two stories. Namely, again, it's easy to tell that's fine. It's easy to tell those parallels briefly as hidden EK symmetry. So the point is that there are deeper parallels, but these are combinatorial parallels between physics and algebraic geometry, namely hidden EK symmetry present in both Del-Pezzo surface BK and 11 minus k dimensional reduction of M theta. On the algebraic geometric side, the symmetry, this hidden symmetry, is coming from the fact that considering the homology, the integral homology of the Del-Pezzo surface, H2 BKZ, noticing that this is isomorphic to z to the power k plus 1. This is just a free abelian group on k plus 1 variables. And it has a natural inner product, actually Lorentzian type inner product given by the intersection pairing Well, first it goes into H4, and then you integrate over the fundamental cycle, and this goes to Z. Right, and the intersection pair, and you intersect basically two-dimensional classes on the complex surface, and this gives you an inner product on this lattice. This is a lattice of rank k plus 1. It becomes a lattice because of this, because it has a natural inner product. And also, this is not algebraic geometry, as you may notice. This is physics, which is also a proper. Sorry, this is not physics. Yeah, this is algebraic topology so far, not just to maybe justify the first justification of the fact that this is supposed to be a homotopy theoretic methods, or this week. Homotopy methods in quantum field theory and quantum geometry, right? Yeah.
So you say Lorentzian, it's just plain negative then?
No. No, it has index negative K1. I mean K1, K negative modes. Each exceptional divisor, the result of blowing up, is a -1 curve. And so its square is -1, whereas the hyperplane class on CP1, on CP2, the CP1 sits in CP2 actually has self-intersection 1. So it has negative K, yeah, so negative K, well, sorry, K negatives, what is it called? 1 comma K signature. 1 positive mode, K negative modes. Still called Lorentzian, right? Yeah. Okay. So this is the topological part of the story, but not of the whole day's story. It will be a much more exciting topology in a few minutes. But this is the topological part of the story. The algebraic geometric part comes in the fact that you have a distinguished class, namely the first Chern class of omega of complex, and let's say holomorphic omega 2 BK, on BK. So you consider the line bundle of holomorphic two forms, the holomorphic line bundles of holomorphic two forms, like dz1 locally, which look like a holomorphic function times dz1, dz2 in local coordinates z1, z2 on the surface. You take its first Chern class, and it's a distinguished element in H2 of BKZ. And so, well, this is often denoted, this is known also to be, also known as the canonical class, let me call it K sub K. Well, maybe I want to take the anti-canonical class. Doesn't really matter. Yeah, the canonical class, okay, that's fine. The canonical class. In algebraic geometry, this is known as a canonical class, and so it comes from holomorphic or equivalently algebraic geometric data on the surface. Not only this is the only ingredient that comes in through topology. And just having this data, you can easily create a root system of type EK. So, namely, a data, a lattice, let me say NK, lattice of rank K plus 1, signature 1K, then yeah, and then the class K sub K, it's actually in this lattice. So and this is a distinguished element in this lattice, gives rise to a root system of type EK. So it's very easy to describe roots. The roots, and they will happen to be of type EK. The root system, maybe I should say root system, is, you consider vectors in this lattice or elements of this lattice, I don't know, V in NK, such that V is perpendicular to the canonical class, and such that V, the square of V with itself is equal to -2. And this gives you the standard, like you can check that this is an EK type root lattice. And this is what I call, and this is how this type EK root system, this is what I call the hidden symmetry hidden EK symmetry in the world of Del-Pezzo surfaces. Namely, this happens for the kth Del-Pezzo surface BK, and it gives you this root system of type EK. So, so in a way, there is some. You can say that sort of the algebraic geometry of intersection theory on Del-Pezzo surface is governed by the symmetry of type, by the symmetry group of type EK, in a way. This is a very classical result, like 19th century algebraic geometry. It's related, for example, for K equal to 6. It's related to the fact that B6 has, it's a cubic surface in P3. It's always, you can prove that B6 is always a cubic surface in P3 and in CP3, right? And has exactly 27 curves, 27 lines, like straight lines. There are 27 lines, like the surface is very curved, but there are 27 lines sitting on it, exactly 27 lines. This is the middle. For a long time, I thought it must be a result of the Italian school of algebraic geometry, but it turned out as one of the authors of this result is Cayley. But it's the middle of the 19th century mathematics. Has exactly 27 lines, and this is related to E6, that the dimension of a fundamental representation of a Lie algebra of type E6 is 27. And it's not a coincidence. It's known, like written in books, for instance, in Manin's book called Cubic Forms. See Manin's Cubic Forms. And Manin once told me that he believes that his name originates from the name of Italian dodgers. Maybe even Florenzian dodgers, but I don't know. Okay, yeah, so this is what happens in algebraic geometry. In physics, let me describe it. I will describe it to you in an example. Maybe I should start with this one. What happens in physics on this side.
Is there a geometric quantization story here where you can derive this representation starting with V6? Like, is there a symplectic structure on V6?
Yes, there is a symplectic structure. It's actually a Kähler manifold, but I don't know.
Okay.
I don't know if it's related to geometric quantization. That's a good point, interesting thing to look at, but I've never heard about geometric quantization creeping in. Okay, yeah, so on the physics side, when you consider an 11 reduction of M theory to 11 minus k dimensions, basically you look at reduction of M theory, you look at the behavior, the dynamics of D-branes, and then you notice the same, basically the same combinatorial pattern arise in there. And it arises in there maybe in the following way. So this is the table that Iqbal, Naitsky, and Waffa had. As I told you, I want to do it in an example. This is type 2A string theory. And here, if you look at branes in space-time, in 10-dimensional space-time, remember, the 2A string theory corresponds to k equals 1. It was actually on this side of the blackboard that I've just erased. So in 10-dimensional space-time, so D-branes in 10-dimensional space-time, you can look at them. Let me sketch a table. There is a brane of D-brane of type D0, then a D-brane of type F1, another one of type D2, D4, NS5, D6, and D8. And if you look at their tensions, tensions, then, well, it would be too long for me to write this down completely, but let me just start on this end. LP, negative cube to the fourth, R inverse to the negative 3, then L negative cube power LP. So LP is the Planck scale, whereas R is the radius of the corresponding to the radius of the torus. In this case, the toroidal compactification is just one-dimensional. We compactify 11-dimensional theory on one circle on a torus of dimension 1, and this is the radius of this torus, of this circle. And so here's LP negative cube 3 to the power negative 3 R inverse to the power 3, and it goes down like I could write to you those exponents of those products of those powers of those LP negative cube and R inverse, and I can go down. But the point is that when Iqbal, Naitsky, and Waffe looked at those tensions for different D-branes, they said, okay, in algebraic geometry, on Delpezza, on this Delpezza B1, we have divisors of type, we have divisors which correspond to, which may be written like this. Well, divisors meaning complex curves sitting in there, or even formal sums, formal linear combinations of complex curves, or you can view them as elements of the two-dimensional homology group with integral coefficients, right? So here it's H minus E. So in this case, just for comparison, H2 of B1 with coefficients in C is Z squared, and it's actually spanned by the class of the hyperplane coming from P2. So there is a map from B1 to CP2, and on CP2 there is a hyperplane H, and you can lift it, pull it back to B1, and it will give you one generator of the second homology group, well, cohomology group. I'm using Poincare duality here implicitly. And then the other component corresponds to the class of the exceptional divisor. So here we have CP2, which is B naught, and then we blew it up, and what happens is that we we blew up one point there, and this means we glue in a copy of CP1 instead of this point, instead of this point, we glue in a copy of CP1, but everything else remained intact. So we didn't change anything. It's a local process, sigma process, or blowing up of a point on the surface. So this thing is called E, like the vertical thing on. So this is our B1, and it maps down to, blows down to B naught. And so on it we have this exceptional curve or exceptional divisor. It's called the exceptional divisor E. And then here we have H. And so the homology group is like this, and the inner product is like E dot E is -1, H dot H is 1, and H dot E is 0. That's the inner product there. And the canonical class is -3, K1 is, yeah, I should have looked at K2 for the fun of it, is E minus 3H. That's all the data which is there. So here I started writing some divisors or second cohomology classes on the Delpezza surface B1. And so those correspond to, this is H, this is 2H minus E. This is the Never-Schwarz 5 brane is 2H. This is 3H minus 2E, and this is 4H minus 3E. So they said, here is the correspondence, like read off those exponents from the tensions of branes, read them off, and create the corresponding divisor on Delpezza. So Delpezza B1, maybe I should put right here divisors divisors on. So these are still elements of H2, of the second cohomology group, and on the surface, and then they correspond to those quantities. So basically what corresponds to is those, oh, sorry, which means I made an error here. This should be, yeah, it should be -2 here. So 3, -2, 4, -3 gives us this. And this exponent is -2 for the tension of the D6 brane in the 10-dimensional space. This is a glimpse on the physical part of the story. And this is how, but the mystery was that they found some things happening in both situations. Like there is a series of objects, on the one hand in physics, on the other hand in algebraic geometry, and those objects give rise to this exceptional series of Dynkin diagrams and root systems, and then the parallels go even deeper because you can create this correspondence, like say this corresponds to that, this corresponds to that, but you have no clue why this happens, why this is happening. So so mysterious duality of Iqbal, Naisky, and Waffa said that like there is physics in terms of toroidal compactifications of M theory corresponds to algebraic geometry, but the mystery was that it's not at all clear how those Del Pietro surfaces are related to physics. Yes?
I must have missed it. What was the meaning of the particular divisors that you wrote on the second line, aside from the fact that the coefficients matched the power factor?
No other meaning. You know, they said, here are those wonderful divisors.
If you think about 2 pairs of integers in the first line, I can write down the corresponding divisors.
Right. Yeah, you can write infinitely many divisors, right?
Well, they're infinitely many divisors. I want to know whether there was some significance to the...
No, yeah, the subsequent works only were able to relate more divisors to like kind of questionable branes, D-branes. But it's not clear why those divisors would correspond to that. You know, it would correspond to those D-branes. No, nobody knew. It was just a mystery, total mystery. They didn't explain why this selection of divisors. They explained we select those divisors because we know there are those D-branes. But those divisors have some properties in common. It's like, I think they're degree 1 divisors, so it means k sub k. Well, I already used d, but d stands here for the divisor. Yeah, I switched to using dot for the inner product. So this is -1. So they're all lines. That's one thing, yeah. Right, but then later on they started creating, looking at other divisors and sort of saying that here are other branes which other divisors correspond to. Yeah. So, and these are degree 1. The degree is coming from negative, pairing with negative k sub k. So degree 1 divisors. Okay, yeah, so, but still the story was largely mysterious, and it still is. Now, let me tell you a bit more. Yeah, I was telling you that this is EK symmetry, like hidden EK symmetry, that for all sorts of k's here, k runs in both situations from 0 through 8. You get exceptional root systems of type EK. But you probably might have noticed, that you know only E6, E7, and E8. Then how do you know what E, say 5 is? D5, yeah. Oh, D5. Oh, very obviously, yeah. It's great to have physicists in the room.
Keep removing nodes from the different diagrams.
Yes, yes, exactly, yeah. So the EK more precisely is this. You sketch the diagram for E8. So this is the diagram of type E8. And then you start cutting it down by those slanted lines starting from the right, and you get E7, which is left on the left and below this cutting line. This is E6. Then when you cut here, you should recognize in the remaining piece D5, so E5 is D5. Then when you cut here, you get E4, which is the same as A4. See 4 nodes like this. When you cut here, this is why the lines were slanted, you get E3, which is A2 cross A1. When you cut it here, you get E2, which is A1. Cut here, you get E1, which is the empty set, yeah, which is the same as A0. And you can keep going. Well, you don't want to go below 0, but E0 is A negative 1. Why? Because this group is SL, I mean, it's the type of the complex simple Lie algebra SL1, and this is SL0. The special linear Lie algebra or Lie group of the zero-dimensional vector space. It exists. It's just equal to 0. Or who knows to what? Yeah. It's just A1. Yeah.
It's just A1.
Yeah. There is no R. Yeah. So you remember this equation here. This is the orthogonal. This defines. So it says V is in the orthogonal complement of K sub K, and this orthogonal complement is of rank K. The whole lattice is of rank K plus 1, and this is orthogonal complement, which becomes a lattice of rank K. And so it all corresponds to this. Yeah. Okay. Yeah. So right. Yeah, but also moreover, when you look at type E2 in this, when you look at K equals 2 in this situation, you would find out it's only one element of the lattice which satisfies. Well, one, and there are 2 elements of the lattice, that one and it's negative, 2 elements of the lattice. Yeah, so, right, yeah, because the root system consists of 2 elements, and the root system of type A1 consists of 2 elements, a vector and it's negative. Okay, so here, all right. And you, no, nobody succeeded in that. Okay, yeah, it's only numerology. It's right, yeah. So now let me tell you something about this. So let me formulate our main result. So basically, the thing is that if you look at this diagram, mysterious relation between physics and algebraic geometry, then what we add to this is a completely explicit relationship between physics and algebraic topology. And still a mysterious conjectural relationship between algebraic topology and algebraic geometry. And this is what we called mysterious triality. Well, still mysterious triality. So basically our piece is this bottom piece, and which is explicitly related to physics, so inexplainable relations of topological, we present a series of topological spaces, which on the one hand are explicitly related to physics, on the other hand, they have manifest EK symmetry. So a series of topological spaces which are not so bad. You start with S4 and you start creating certain loop spaces related to S4. Namely, S4 is the four-dimensional sphere, right? So LC S4, then LC squared S4, then. So instead of blowing up in algebraic, like we do in algebraic geometry, you keep doing iterated loop space construction. The LC is not just the usual loop space. I will tell you in a second what this is. And you go through to LC8 S4, and then you can stop if you wish. We notice what happens there, why you may wish to stop, even though you can continue, of course, taking loops, iterated loop spaces. And here there is some, again, an outlier story, which is type 2B model, which we know what this topological space is, but it's, I mean, we can describe it in a certain way, but it's not as nice as one of those topological spaces, as any of those topological spaces. So here, loop spaces, those loop spaces are defined as follows. LC of a topological space Z would be, you consider the mapping space from S1 to Z. That's known as the free loop space, often denoted by LZ, the free loop space. And so it's the space of like strings in positions of strings in the topological space Z, in the given topological space Z. And then you mod out by the action of S1 by rigid rotations of the source. So in a way, you can view this as unparameterized free loops or equivariant free loops. So you kind of kill the big chunk of parameterization, basically. You don't know where the beginning of this loop is, which is actually what you expect to if you want to talk about just loops in a space. So think of them as strings. So these are just strings sitting and pieces of closed strings sitting in Z. And we mod out by, so this modding out by the action means, in principle, you can mod out by the action S1 acts by rotations here, but there are some fixed points of this rotation action. And we want to sort of create some nicer quotient without fixed points, and for this reason we take the homotopy quotient. So you can use the Borel construction or your favorite construction to create a homotopy quotient. So the fixed points of the S1 action are, for instance, constant loops. Like if the loop is constant, no matter how you rotate it, it's the same loop. And so, those points create some not niceness of this quotient, and so when you take the homotopy quotient, we use a homotopy theory trick to get rid of it. Okay, and so these are those spaces. Another thing is we should take a connected component of this mapping space, of the constant loop in this mapping space. Because, say, for instance, if Z has non-trivial fundamental group, then this mapping space will be disconnected. We'll create homotopy. We'll create path components, and so so we want to take just the component of the trivial loop here. And so this is what we denote by LCZ. So we call it a cyclification, or oftentimes this is called cyclic loop spaces. Cyclic loop space. So this is the free loop space before taking the quotient, and this is the cyclic loop space. Or sometimes it's called equivariant loop space, the equivariant loop space. We call it also cyclification of Z, the cyclification of Z. And so you get this sequence of spaces, and then a sequence of spaces, and such, our main result is to show that how it is, the sequence is explicitly related to the physics side of the story. So maybe I should say, via rational homotopy theory, RHT, we study, we show two things, that these spaces have a manifest EK symmetry, and are explicitly related to 11 minus k. Well, maybe I shouldn't say these spaces. The kth space, the kth, I want to fix the k. The kth space, LCK, the k-fold cyclification of the fourth sphere, has manifest symmetry and is explicitly related to the 11 minus k dimensional space-time. Space-time and the dynamics of supergravity. In it, in this 11 minus k dimensional space-time. And then, of course, there is a conjectural relation to del Piazza surfaces, but this kind of completes part of the story, because we have an explicit explained duality between physics and mathematics, but only in the form of algebraic topology, not quite in the form of algebraic geometry. Okay, and so let me tell you what else is going on. So let me explain some of those things. So one of them is called hypothesis H by Hisham Sati, and so another advantage is that this EK symmetry is manifest, unlike in the previous two situations. Like there is an action of a Lie group of type K on the rational homotopy types of those spaces, of the kth space out of this sequence. So maybe let me explain the second part. Start with the second part of this story, relation to supergravity in 11 minus k dimensions. Relation of LCK S4. Yeah, I said this, but maybe it's so easy to write. So why don't I write it down like this? So k plus 1 z sub c is by definition L sub c of L sub ck of z. So that's what it means to take the to iterate this construction. So it's the iterated cyclic loop space. Okay, so the relation to supergravity. Let me start with k equals 0 first, and say that let's consider 11-dimensional supergravity. So the thing is that really we realize that you don't need the whole power of M theory, like all the structure of M theory or type 2A string theory to do those things. It's actually the reason why this symmetry shows up lies kind of in this supergravity background. And so we are looking at really supergravity and just the bosonic sector of it. So we have 10-dimensional space in two fields, one of degree 4 and one of degree 7, which are just differential forms of those degrees. They belong to the drum algebra of the space-time. It's 11-dimensional, sorry. 11-dimensional space-time with two fields, differential form fields of degree 4 and 7 respectively. They satisfy the equations of motion. So their dynamics is described by the equations of motion, equations of motion of 11D supergravity. And these are dg4 equals 0. That's a closed form. dg7 equals -1/2 g4 wedge g4. And star g4 equals g7. This is the Hodge star, which turns 4 forms into 7 forms, because our space-time is 11-dimensional. And this is the Hodge star. We assume there is a metric there, and this is why it's supergravity. And then we have those equations. So if you, on the other hand, look, so this hypothesis H, actually, yeah, I mentioned it in words, but yeah, so hypothesis H notices hypothesis H of Hisham Sati, of an older work of Hisham Sati, notices this, that if you look at the 4-dimensional sphere and apply the first rational homotopy theory construction to it, you get the following Sullivan minimal model. So rational homotopy theory attaches to every topological space a certain differential graded commutative algebra called the Sullivan minimal model, M of S4. So it's just a differential graded commutative algebra, a DGCA, as we say. And this is the algebra over the rational numbers, Q, on two generators, G4. It's a graded commutative algebra on two actually free generators, G4, little g4 and little g7. But it's a differential graded commutative algebra, so those are free generators. So you can think of this as the algebra of polynomials in G4 and G7, but remember that G7 is odd, and so it's actually skew polynomials. It's like, think of it as a Grassmann variable. So it's a graded commutative, free graded commutative algebra on those two generators, such that, but the differential is given by dg4 equals 0 and dg7 equals -1/2 g4 squared. And so the surprising thing is the hypothesis H says that I can go here. Hypothesis H of Sati says that observes that when you have this, you immediately have. Did I do all I wanted? Yeah. It's part of rational homotopy theory. So rational homotopy theory, it tells you that there is a map, there exists a unique, well, let me put it in parentheses, unique up to rational homotopy. Let me put the uniqueness sign, the shriek in parentheses, unique up to rational homotopy, rational equivalence. Yeah, rational equivalence. Yeah, it's fine to say rational homotopy. Map from our 11-dimensional space-time to the 4-dimensional sphere. If I put the 4-dimensional sphere here, I'm cheating a little bit, but it's actually, to be completely precise, we should take what is called the rationalization of the force sphere. It's a space which is rationally homotopy equivalent to S4, but has homotopy groups being Q vector spaces. But it's rationally homotopy equivalent to S4, so it's another incarnation. So you actually have a map to this guy instead of that guy. So, but it has the same rational homotopy, the same rational homology, and it's rationally homotopy equivalent to S4. So in rational homotopy theory, it's indistinguishable from S4. And even to be more precise, it should be, well, rather to this space, or even to be more precise, to its rationalization over the reals, which is another construction of rational homotopy theory, which I don't want to talk about. It's over the reals because these are forms which are defined only over the reals. It's not rational form on X. It doesn't even make, well, one can talk about rational forms on the space, but it's not rational forms on the space. It's just usual differential forms on this 11-dimensional real smooth manifold, which is our space-time. And so there is a map such that, let's call this map phi naught because it corresponds to k equals 0, such that phi naught star of little g4 is capital G4, and phi naught star of little g7 is capital G7. Okay, so there is a unique map up to rational homotopy which pulls back those classes. Well, 4-dimensional sphere is not the usual de Rham cohomology, which is the Salvan minimal model made of, but it may be realized as differential forms on this rationalization. And so those forms from the rationalization pull back by this actual map to those fields in physics. Okay, and this becomes even more amazing when you look at, yeah, another thing is that when you go from, oh yeah, it's time for me to stop, I suppose. Do I have any time left, or 5 minutes? Yeah, I think we started a little late. Yeah, so thank you. So there is a map from X to S4. I mean, if you take a map from X to S4, then it immediately creates another thing. If also on X there is an action of S1, and so this is what you have in those toroidal compactifications. You think of your space-time as either having an action of S1, or more naively, if your space-time is, say, the 11-dimensional Minkowski space, then you compactify one direction. It becomes some kind of a cylinder, R10 cross S1, and you mod out by this S1, you get R10 left. And this is your Euclidean space. So this is your new space-time when you consider toroidal compactifications or reduce dimensions from 11 to 10. And so this immediately creates a canonical map from here to here. And this comes out of an adjunction maps from the total space of a space Y to Z. Well, I should have started, sorry, I should have started here. Maps, so this comes from the space, from a junction. Two functors are adjoined. Maps in the category over BG, so the category of bases of principal G bundles, topological spaces which are bases of principal G bundles. Maps from Y to LCZ are in natural bijection with the space of maps, a set of maps from the total space of Y to Z itself. And so this is the Y we are talking about. It's the base of an S1 bundle if we assume there is an action, a free action of S1 on this space. Then this becomes the base of an S1 bundle, so it belongs to this category. Well, for G equal to S1, it belongs to this category, and we are looking at maps from here to here, and this is in bijection with maps from the total space of this base of a principal G bundle to Z. And so this is the total space, and we have a map from X to S4, so we can go from right to left and create this map automatically. And this construction iterates. Like if you assume that there is also another S1 acting on this space, and this is how you do dimensional reductions or toroidal compactifications in physics, you mod out this space by another copy of S1, then it creates a natural map from X divided by two copies of S1, or this. LC squared S4, and so on. All of those properties, the generators of the Sullivan minimal models pull back. So this is my map phi 1, that was phi naught. This is phi 2, and so on. That the Sullivan minimal models which have certain generators and relations for their differentials, they pull back to the fundamental fields of the corresponding supergravity on this side, and such that, they pull back to those. And the thing is that the dynamics of supergravity in those dimensions, like 10, 9, and so on, the dynamics of supergravity is always given by the equations defining the differential in the Sullivan model. So in the remaining minute, I would write to you one example with what happens, for instance, for the type 2A situation, that is 10-dimensional supergravity, which corresponds to type 2A. So this is type 2A. So the minimal model of LC squared, LC S4, we just go down to 10 dimensions. So it has its Q generated by elements G4, G7, S G4, S G7, and W. Satisfying the relations, well, let me put the relations here, DG4 equals SG4 times W, DG7 equals negative 1/2 G squared, G4 squared plus SG7 times W. So these are forms of degree 4 and 7, I mean, elements. This is an abstract differential graded commutative algebra. Differential graded commutative algebra. These are forms of degree 3, and this is a form of degree 6. Oops, degree 6, and this is degree 6, and this is degree 2 form. And then DG4, DSG4, SG4 is just one symbol, one generator, equals 0. DSG7 equals SG4, G4, DW equals 0. And so if you rename those in supergravity, like supergravity of type 2A, you have the equations dF2 equals 0, dF4 equals H3 wedge F2, dF6 equals H3 wedge F4, and finally dH4 equals well, I should continue here, equals negative 1/2 f4 wedge f4 plus f2 wedge f6. So these are the sort of, they're called duality symmetric equations of motion, duality symmetric equations of motion, of supergravity in 10 dimensions, of type 2b, type 2a, sorry, supergravity of type 2a in 10 dimensions. And so this is sort of the kind of a glimpse on the reasons of why those topological spaces are related to physics. So you can go to any k, like if you want me to write down the equations of motion of 5-dimensional supergravity, that is 11-dimensional supergravity reduced to 5 dimensions, then I would, there is a recipe of how to write this down, coming from mathematics, coming from creating the recipe for writing down the Sullivan minimum model of the cyclification of a space once you know the Sullivan minimum model of the space that you start with. And so you can just iterate this construction of the Sullivan model of the cyclification several times, and you obtain some equations. The number of equations grows dramatically, like you see here. There are so many equations as compared to the 11-dimensional case. But in physics, they were obtained in hard way. That is from the Lagrangian and writing down the Euler-Lagrange equations of the corresponding Lagrangian. And you know, it's a very long story in physics, but here it becomes very quickly an easy exercise for a rational homotopy theorist like me. That's it. Thank you very much. By what? Right.
Seems like I got this same equation as I said.
Yeah. So the point is that what physicists do to create those equations, if they go as through reductions, is the same procedure as mathematicians do when they take cyclifications, cyclical spaces.
Okay.
Yeah, so I'm not. Yes, you're saying it's not so powerful. Yeah, so Hisham told me that it's pretty hard to write down the equations of, say, 5-dimensional supergravity. You know, I mean, even they're organized their own way, because, like, why is this H and why is this F? You know, here there is some hint on what's going on, and on
This
the.
this part is the full equations of motion involving the metric and the fermions and the
But in this case, it doesn't need to write the.
No, but this part,
Yeah, that's easy.
this part is easy, right?
Yeah, but if you go down,
No, this part remains.
even if you go down to 3-dimension.
Remains easy.
Okay.
But the full thing, yeah, it's horrible.
Mhm. Yeah. So the thing, um, we can write also this manifest EK action on those spaces, and on the physics side, it's interpreted as the symmetry of the equations of motion.
No, but don't you,
Yeah.
for instance, in the supergravity,
Yeah.
there's a continuous EK symmetry, right? And the non-compact form of EK acts by isometries of the scalar manifold. Here we haven't written down anything to do with the scalars. remnant of it. But
EK symmetry is a scalar.
manifest symmetry of the equations of motion of the scalars, or the action, which you write down for them. Because the scalars parameterize this coset, split real form of EK modulo the maximal compact subgroup.
Mhm.
So, E8 mod SU8, right, in 3 dimensions? Right. Right, so.
Yeah.
I guess the one, the Maharishi, like in the day, was E77, the 40 n equals 8 supergravity. But you haven't, for instance, written down the equations of motion for the scalars, so we don't actually see the manifest continuous.
Yeah, nevertheless, here there is a manifest EK symmetry.
In what sense?
Like there is an action on this algebra, on this differential graded commutative algebra. There is an action of EK of the Lie group real form, split real form of of the type E77. Sorry, not even 77. Well, in this case, it's one, but whatever. Yeah, EKK. Yeah, there is an action of EKK on this minimal model.
Maybe that would be good to understand. I mean, what does that look like?
So.
I mean, all these things have different degrees, right?
Right. Yeah.
So how does EK act on them in some interesting way?
Yeah, in an interesting way. Like EK has generators like this. It has Chevrolet generators like EIs, FIs, HIs, and it acts on them in a certain way. I guess I should write it down later for you. It's just an explicit way, because it actually all started with first noticing an implicit EK symmetry. That is, first we noticed in our papers that are on the internet, we noticed that the Cartan subalgebra of the Lie algebra of EK acts on those generators.
Sorry, now I understand. If you look at the lattice
Some people are quick.
for all of these P-form gauge symmetries, the lattice of charges is acted on, is in the fundamental representation of EK.
Yeah.
Right? So in the 4D n equals 8 supergravity, it's E77, and the lattice of charges is the 56.
Yeah.
And so it is, okay.
Yeah.
I see. In that sense.
Right. Yeah. Yeah, we also find like 27 lines on on the six-fold cyclification of the four sphere. Like there are actually like distinguished homotopy classes of maps from the two sphere or CP1 to those spaces. And also, if you look at those maps, those spaces play the role of universal target spaces for space-time, for supergravity in the corresponding space-time. They are universal target spaces. So basically, they contain some essential information for some basic part of supergravity on this side. These are sitting in the form of those Sullivan minimal models here, the equations of motion of supergravity, and they pull back to the equations of motion via those maps, and so it's really a nice story. So it's those spaces encode in a way through those differential graded commutative algebras the homotopy types of sorry, not the homotopy types. They through their rational homotopy types, through those DGCAs, they encode the equations of motion of supergravity. Well, part of the equations. It's called duality symmetric part, as Hisham taught me to say in this situation.
What about the relation to Delphi?
Still a mystery.
Okay.
Yeah, we are working on it, but for the moment, it's still a mystery. we anticipate that it will be a relation of the type like maybe geometric length correspondence, like one space is the modular space of some stuff for the other space.